Good morning everyone. Thank you for joining Mr. Ish on this second video on derivatives. Today we will be talking about the chain rule for derivatives. The chain rule can be applied to any kind of derivative function. As of now, I've only talked about calculating derivatives of polynomials, but you could apply this chain rule for any kind, and you can apply it for trigonometric functions, exponential functions, logarithmic, hyperbolic, anything. Having a given specification to that function, if it were to merit the requirement for using this chain rule, then you would use the chain rule. There's basically three rules we have to go through as we get into the derivatives. One will be the topic of this video, chain rule. The two rules we have to talk about are the product and the quotient rules. If you think back to the video I presented on polynomial derivatives, the polynomial function derivatives, you know I've only talked about adding and subtracting functions in that video, and then using the addition and the subtraction of functions for the derivative calculation. But there you can also do derivatives of functions which involve products and the quotient of various functions. But that'll be a subject matter of another video. When we're talking about the chain rule, we're looking at something which looks kind of like a chain. You want to be thinking about composite functions, because if you have a basic function, you don't need to employ the chain rule. You only have to employ the chain rule where you're trying to determine the derivative of a composite function. And for example, in an exemplified manner, if I told you to find the derivative of 4x cubed, you don't need to involve the chain rule. Now you're thinking in your head, what exactly is this chain rule? I'll get to that. But if you had some function which looked like this, you don't need to do the chain rule because it's not a composite function. But if supposedly I asked you to calculate the derivative of something which looked like this, you might want to be thinking about using a chain rule. And remember, here I'm only presenting polynomial type functions. What if there was a question and you had to determine the derivative of something which looked like this? Here you have a composite function. This right here is another example of a composite function. Let's put another thing over here. Something as simple as this, sine square 2x, and someone told you to find the derivative of this. It's a composite function. You don't know how to calculate this because I haven't talked about derivative calculations of trigonometric functions. But once you learn the chain rule for polynomial functions, you can easily apply that same application to any kind of function after that. So all you have to do right now for chain rule, and then in the next two videos, the product and the quotient, which could probably just be one video, but anyhow, for the chain rule, the product rule, and the quotient rule, once you learn it in the most basic form for the polynomial derivatives, you can easily apply that same knowledge to any kind of function afterwards. So let's look at what exactly the chain rule is. So the general procedure for using the chain rule, and it does not involve only just two links, it can involve a number of links. But the general procedure is whatever function you have, and you have to find the derivative of that function with respect to x, but you end up dealing with a composite function. You have to break that composite function and do the derivatives in pieces. But each of those pieces are always in a multiplication format. Here is an example of a function which would be a composite function. Look over here, 2x squared minus 1. It's a composite function because it came from two different functions. One was a function was just basic 2x squared minus 1, and the other one was basically a radical of that, a square root of that. So you have a composite function here, two functions being composited into a single function. When you have something like this, you have to be thinking about the chain rule, because if you don't, what can you do? You can convert this radical into something which looks like this with an exponential power, and then you try to do the d over dx. And if you remember the format for a simple polynomial derivative which had the expression this, you would multiply the b with the a, and then you would reduce the exponent by 1. Remember this format, the topic of the previous video? Well, if supposedly you didn't use a chain rule, let's try to do this and see what happens. You would multiply 1 or 2, but this entire thing is an expression. You can't open it up yet. And then you take this 1 over 2 minus 1, but you still are not really getting anywhere because you haven't addressed the items within the parentheses. You haven't clearly addressed the items with the parentheses. You're just working here in the boundaries without really affecting the items in here because you have an expression over here. It's not like a single term, it's a composite function. And that right there creates the problem, but the solution to that problem is a chain rule. So let me show you how the chain rule actually applies when you're dealing with composite functions. So let's create a little bit of room over here. If our function f of x, for which you have to determine the derivative, is this 2x squared minus 1, and we know now that it is a composite function, we just have to split it up. And the procedure for splitting it up is in this format over here, and you don't have to worry too much about these letters and their notation. Just learn how to actually do it, and that would be good enough. Think of this as two composite functions. As I split it before, this right here is your one composite function, one function here, and then the radical serves as your other one. So you have to make a substitution, and this is a substitution you want to make. Let u, the letter u or any variable, equal what you see inside, 2x squared minus 1. If supposedly we did this substitution, then essentially you're looking at something which looks like this, aren't you, right? Because the u is representing 2x squared minus 1. Then your function really is basically just u root, square root of u. You basically, by means of substitution, simplified your composite function into something which looks like this. Now look at what I'm doing. I'm going to take the derivative, right? I'm doing this first part right here, the derivative right here, the first part. Let's look at this first part. And you have simplified the composite function into something like this. This, you know, you can easily do a derivative of, because this is just u to the power of 1 over 2. Now let's bring in this other part. The other part will be actually representing the substance of your substitution. Alright, du over dx, where we now look at just the derivative with respect to x. The first part was a derivative with respect to your u. The second part is your derivative with respect to x. And here you just plug in the item of the other, the underlying part of the radical. Remember, this is a composite function which came from two parts. The first part was this 2x squared minus 1, and the second part alone was the radical. Well, in the first part of your chain rule, you dealt with one of the items of the composite function. In the second part, you deal with the other item of the composite function. And now you do your individual derivatives, and you proceed in that manner. So this will become rewritten in a more friendlier format as u to the power 1 over 2, and you don't need to rewrite this second part because it already is in a good enough format. And now here you just use this formula right here, this formula, to do the rest of this. When you take the derivative of this, you'll take individually derivatives of this and derivative of that. You'll do 1 over 2, you'll multiply it over here, and you'll reduce that exponent by 1, just like that format shows you. So this will become 1 over 2 u to the power of minus 1 over 2, and then this right here, 2 will come over here, because everything is multiplying. 2 times 2 is a 4, and the exponent will be reduced by 1, which is just a 1. And you know from the previous video, derivatives of all constants is always 0, so you don't have to do anything else with that minus 1. Now combine everything and simplify where you can. This 2 simplifies with this 4, and you get a 2. You get left with a 2x over, you see this u to the power of minus 1 or 2? This is really root u, because it's a minus, it's a reciprocal, you bring it down, and it's a 1 or 2, so it's a square root. Now in the final step, all you have to do is substitute what u was, and you're done. And you know what your u was simply from this step over here. So your final answer should look like this: 2x divided by root of u, which is 2x squared minus 1. 2x squared minus 1. And that right there is your final answer. So the derivative of this function right here by means of the chain rule is this: 2x divided by square root of 2x squared minus 1. How you proceeded through this entire process is chain rule, and how you actually apply the chain rule is by means of a substitution, which splits your composite function into your two sub-functions, for which individually you look at their derivatives, and you marry those back up after you've done your derivative calculation, resubstitute back what you had, and you present your final answer. Now it may look a little complicated, and the only way to overcome that complication or that mental barrier that we might have in our head is by doing more practice questions. And here's another such example. Remember, we're applying chain rule for any kind of functions. They don't have to be polynomial functions alone. They can be trigonometric, exponential, whatever. Any kind of function, so long as it's a composite function, you want to be thinking about a chain rule. Now you know this here is a composite function because it could have come from two subfunction. If f of x was equal to x to the power of 5, and we know g of x was equal to 2x squared minus 5, and our question was f of g of x. You know f of g of x would be g of x plugging into place of x, and that right there would individually provide you with this. So you know here you're dealing with a composite function of two separate functions. So how you want to deal with this? Start with your substitution. Let u equals what you see in here, and you can do your substitution however you want, but this is how I'm going to do it. Let u is equal to 2x squared minus 5. Therefore f of u is equal to really u to the power of 5, because this thing is actually being affected by an exponent of 5. Now you actually do your derivative part, d over du, the derivative with respect to u, I should not be putting an equal sign over here, the derivative with respect to u, and then the derivative with respect to the x component, 2x squared minus 5. Now do your individual derivations using the formula you know from the previous video, where the exponent becomes attached with the coefficient of your variable and the exponent is reduced by 1. So you get 5u to the 4 times, it's always in a times format. Now you have to look at these individually, because this right here you can separate them out as derivative of 2x squared minus the derivative of 5, but you know derivatives of constants are always 0, so you're really looking only at the derivative of 2x squared. The 2 multiplies with this 2, you get a 4, and the exponent 2 is reduced by 1, so you get a 4x. When you marry these together, you get 20x u to the power of 4, but you gotta resubstitute your u. You have to resubstitute it. You get 20x, and u happen to be 2x squared minus 5, but now to the power of 4. So this right here is your final answer using the chain rule. So look again, the chain rule requires several items. Item number 1, recognize you're dealing with a composite function. Item number 2, start with the substitution. Item number 3, create your chain derivation rules, you can call it that. And item number 4, do your actual derivatives for the individual items, the individual sub-functions which you have separated. And lastly, item number 5, bring everything back together and resubstitute to obtain your final derivative for what you need. Alright, for what you need. And remember, here I'm presenting you examples so far which have involved only a chain of 2 items. You can have a chain of several items, and at the end of this video I might show you something like that. So here we have a function, we can just call this f of x is equal to 4th root of this polynomial. And you know, for this video, chain rule video, I'm only using polynomials because we haven't learned the derivatives of other functions yet. So we're just sticking to topic on that, but that's fine. Once you learn the procedure of chain rule, you can apply it to any other type of function. And you know the chain rule is going to be applied to those functions which are composite functions. This right here is a composite function of this function, which is within another function which happens to be the 4th root. So once you can make that recognition, you can start with your substitution, and the substitution will be this. Let u equals what you see over here, 1 plus 2x plus x cubed. Therefore your function, you know, f of x now is f of u, really has become 4th root of u, or you can just say u to the power of 1 over 4, which is the same thing. 4th root or 1 over 4 exponent, same thing. This right here is a better way of saying it. Now do your separation, the derivative with respect to u, you do u to the power of 1 over 4 multiplied by with the derivative with respect to x, and you have all of this over here, 1 plus 2x plus x cubed, which you know you have to now individual. This right here is no different than what you were seeing in my previous video, the derivative of polynomials. But you're going to do individual derivatives of everything you see over here. U to the power 1 over 4, 1 over 4 will multiply with the exponent, with the coefficient you see here of a 1, and the exponent will be reduced by 1. You'll get 1 over 4 u to the power of minus 3 over 4. Minus 3 over 4. And these derivations or separation of derivatives are always in a multiplying format over here. For this video, you can do the derivative of this, the derivative of this, and derivative of this. Constants are always 0. 0 plus 2x. Derivative of that will be just a 2, because this is x to the power 1. 1 multiplies with this 2, you retain the 2, but becomes x to the power of 0, which is just a 2 or staying behind. The 3 multiplies with the coefficient of x, which is the 1, so you get a 3x, but the 3 of the exponent is reduced by 1, as you know from the formula, it becomes a 2. Now you gotta marry it up. By marrying it up, I mean you're putting it in your close to your final format. Here's your numerator. Here you can have a denominator generating. Look over here. It'll be 3x squared plus 2 over 4, which is in the denominator, u. This thing is coming in the denominator because you have a minus exponent. Minus exponent means 1 over. So you can have u to the power of 3 over 4. We just have to write this in a proper final answer, and when we do that, we're done. So our final answer is going to be this with the resubstitution of u. 3x squared plus 2 over 4. Let's bring our radical sign. This is 3 u to the power of 3 over 4. So you know we're dealing with a fourth root. But what exactly was u? U was what we substituted right over here. 1 plus 2x. See, 1 plus 2x plus x cubed. But this is all to the power of 3. All to the power of 3. Because it was u to the power of 3 over 4. And this right here is your final answer. Not too hard. If you didn't want to use a radical, you could have written 4 times this entire thing right here, this expression to the power of 3 over 4. But I brought back the radical. Nothing wrong with doing that. But this right here is your good final answer. Again, you start with a composite function. You recognize that as a composite function. Make a substitution. Do your separation, the chain rule separation, individual derivatives which are always multiplying with each other, and then your final answer, which involves a resubstitution back for your original substitution. So take a look at this question over here. Now remember, you know I'm being a little restricted and limited here in terms of the examples I can present, because we've only done derivatives so far of polynomials, but on top of that we haven't talked about the chain rule in terms of the product rule and the quotient rule applying along with the chain rules. We haven't even talked about the product and the quotient rule. So we're limited here in terms of the types of questions we can provide, but that's fine. You're learning here only the basic procedures. But keep in mind, when you have most of these derivative questions, you'll have multiple things occurring in the same question. You can have a function which is not necessarily a polynomial function, and it's a function which will involve a product rule and the chain rule, or you can have the quotient rule applying with the chain rule, or you can have all three types of rules, the quotient, the product, and the chain rule, all applying the same question but in different parts of that same question. So you can have those types of complexities kick in. But let's look at this question over here. If you're looking at this, you're thinking about a function which was really f of x was equal to x squared minus 4x plus 3 to the power of minus 1, because this to the power of minus 1 was rewritten in this format. Nothing wrong with saying that. And you know this right here was a composite function which could have come from the following items. If f of x was just x to the power of minus 1, and you know g of x was equal to x squared minus 4x plus 3, then technically we're looking at a situation of f of g, a composite function where the g function was plugged into the x function to give you this, and then this part right here was rewritten in this format. But which format over here do you think is a better format? In the way I've written it here or the way I've written it here? I believe this way right here is a better way, because you actually have the exponent laid out to you and you can do your substitutions more easily. So let's look at it in that, let's look at this question in that way, and let's rewrite it out. D over dx, and then we're determining the derivative of this function to the power of minus 1. And you know we're dealing here with the composite function and we're dealing here with the chain rule. So let's start with the substitution. U is equal to what we see over here, x squared minus 4x plus 3. Therefore, f of u is equal to u to the power of minus 1, right? The same thing to the power of minus 1. The composite functions is what it's all about. Now let's do the derivative part. Derivative with respect to u to the power of minus 1, multiplied by the derivative with respect to x, which is your actual substituted expression, 4x plus 3. Now you know you got to find the derivative of this, and you have to find the derivative of this. U to the power of minus 1, what do you think that will be? Well, you know you'll take minus 1 as an exponent and multiply by with the existing coefficient, which is a 1. So you'll get a minus u, but this exponent will be reduced by 1. It'll become a minus 2, right? And you know you got to look at the individual derivatives of all of this, but constant derivatives are always 0. You can just cross that out. X squared will become 2x. 2 multiplies with that coefficient of 1, and the exponent is reduced by 1, so it's 2x. This minus 4x will become minus 4, and you know why. The exponent on x is just a 1. 1 multiplies with that 4, and you get a 4, and the exponent is reduced by 1, becomes x to the power of 0, or you can just say minus 4. And you know that derivative of polynomials was the subject of my previous video. Now all you got to do is finish this up. Minus u to the power of minus 1 over 2 is really saying minus 1 over u squared. minus 1 over u square. You're still multiplying this with 2x minus 4. 2x minus 4. Now all that remains is to present a final answer, and to do that we will make a little bit of a space right over here, a little space creation, and we'll present that final answer. And the final answer will involve resubstituting your u back over here and writing everything in a proper rational function format, numerator and denominator. This is going to be my answer, minus 2x minus 4. You see we have a minus 1 and multiplied with the 2x minus 4. We have our denominator line, we'll put the u value back. X squared minus 4x plus 3 square, and this right here is my final answer. So the derivative of this rational function is right over here, and you're seeing it before you, derived through the process of using the chain rule, which of course you would have to have demonstrated the recognition of a composite function at play. Before I close out my video, I want to reiterate why we have to even bother with the whole procedure of chain rule. And this is why, because it simplifies very greatly the derivative of a very complex function, or maybe it doesn't even have to be very complex, but of a slightly complicated function, the derivative of that can be quite easily performed. If someone told you to find the derivative of this, now a person out of stubbornness could say, if I were to just do 2x minus 4 times 2x minus 4, and then 2x minus 4, and then 2x minus 4, you know, the same item being multiplied 4 times, and then when you open all of this using the FOIL and whatever methods you want to do, you end up getting a polynomial, and now you know you're basically back at the starting point, and you can easily do the derivative of the polynomial. You'll have pluses and minus, but that's fine. You'll do the individual derivative of each of those items, just like how we did in the very first video, and you could say you'll still get your final answer and you're done. And you can do this very long process, or you could do this using the chain rule and greatly simplify the entire need for doing all of this. Why is the chain rule superior to all of this? Why is it superior? Because first of all, there's less likelihood of making errors. Imagine you're doing all of this multiplying, you might be bound to make some sort of error because you're doing too much multiplying here, like binomial multiplication is just not easy. You could use a binomial theorem, but still you would be prone to making an error. If you use a chain rule, just using the function substitutions, it makes it so much easier. And I want to show you how this whole process is just made easier because of that. You just have to recognize, the only hard part was just recognizing you're dealing with a composite function, and you would have to make a substitution, 2x minus 4, and f of u was equal to u to the power of 4. I was going to make like a little error over here myself, but u to the power of 4, and then all you had to do was just your substitution, d with respect, the derivative with respect to u is u to the power of 4, and then the derivative with respect to your x value, 2x minus 4, and you could carry this down, 4u cubed is your derivative over here, and the derivative here is 2. You just multiply this and you get 8u cubed. When you resubstitute back the u value right in here, u value in here, you get 8 2x minus 4 to the power of 3, and that right there would be a very easy answer. Basically only took you 2 steps, 2 lines, but doing it the other way by expanding everything out and then doing it would have been just too cumbersome. But this is why you have to use the chain rule, or why you should learn to use the chain rule, because it's just easy. So this last question of ours will bring us right back onto track for this video, the chain rule video. We're going to be basically finding the derivative of this function. Now you know this is a composite function. Just as a breakdown of it, if supposedly f of x was equal to root x and g of x was equal to x plus root x, and you had to supposedly construct the composite function f of g, which you could see as f of g of x, you know, if you were to plug all of this into here, you'd end up with this composite function. So we know we're going to basically have a 2-step chain rule process over here, and you're going to start with the substitution. Let u is equal to all of this you're seeing underneath, x plus root x. Therefore f of u is going to be root of that u. Now let's create our derivative chain. Derivative with respect to u is equal to root u times the derivative with respect to x, what you see over here, x plus root x. And you'll see this question, which seemed seemingly difficult at the beginning, is actually easy. Now you know over here you don't have a composite function. We can rewrite everything in a very friendly format, u to the power of 1 over 2, and then we can do du over dx x plus x to the power 1 or 2, and everything can be easily finished over here. When you find the derivative of this, you get 1 over 2 root u, because this 1 over 2 is going to multiply with the coefficient over here, and the 1 over 2 will be reduced by 1, you'll get 1 over 2 root u, and you can calculate that yourself. You get over here derivative of this, x will just be a 1, this 1 will multiply with the coefficient here 1, and the 1 exponent will be reduced by 1, it will become 0, so you're just left with 1, and x to the power 1 over 2 will very easily give you 1 over 2 root to the power of x. When you do so many of these, you'll start recognizing common terms. Anything you have a variable to the power 1 or 2 will always present you an answer like that, 1 or 2 root that variable. So bring everything together. Actually, before bringing everything together, let's do a common denominator here within the parentheses. We have 1 over 2 root u, and we'll have a 2 root x, and then we'll have a 2 root x plus 1. You see how we've married this up into a common denominator and a fractional term? Now bring everything. In the process of bringing everything, we need to create some space over here to finish this question. Let's look up over here. We're going to multiply the numerator with the numerator and the denominator with the denominator. On the top, we'll get 2 root x plus 1. In the denominator, we'll get 2 times 2. The coefficient of these radicals coming together is a 4. Then you'll have a root x and a root u. But you gotta resubstitute this u value over here. But before I do that, I want to rationalize this root x. I'll multiply the root x on the top and the root x on the bottom. I'll get, and I'm going to multiply these out in one step. You get 2x plus root x over this root x with this root x will just give you a simple x with a root u. And now let's put our final answer with the substitution of this value for u right in here, and we'll be done with this. 2x plus root x over 4x root x plus root x, and that should be our final answer. Seemingly hard question, but not too hard. The algebra part was perhaps more involved than anything else. So keep in mind the chain rule is very important when you're dealing with composite functions. Try not to tackle composite functions without using the chain rule, and the chain rule can get complicated if you have many kinks in the chain, and the chain rule can get complicated when you start bringing in the multiplication and the quotient formula within the same question that requires a chain rule. And those will be types of questions which we will be seeing soon as I talk about the quotient and the product rule. So just as a bonus, I'm going to present you a question on a chain rule which shows how prolonged or how elaborate it can become, where the chain has several kinks or more than 2 kinks, as we have been showing. You can have several kinks show up into this chain. Several substitutions will play into this. And I know I'm presenting an example over here which involves functions which you are not familiar with in terms of their derivatives, because all I've talked up to now are polynomial derivatives, but that's fine because this is just an example. This is just an elaboration. That's all what it is. But I promise you this will not involve the product or the quotient rule. It's just going to be a chain rule, but slightly more complex. So when you're looking at this, you know you're looking at a composite function, and this composite function may have several sub-functions in it, and therefore we'll be doing several different substitutions with it. So when we're looking at this, I want to make this initial substitution. I want to say let u is equal to sine tan 2x. Therefore my first part of the composite function should just be u squared. If supposedly all of this u is u, then you know you're dealing with the u square. So you're going to look at something like this: derivative with respect to u square, and then the derivative with respect to everything else you have left with is presented right over there, sine of tan 2x. Now when you're looking at this, you know you're not done because you still have a composite function. You basically have to run the chain rule through for your derivative for your given function till the end, where you no longer are left with a composite function. But we have a composite function over here, so we have to make another substitution. And now this substitution means we're adding a kink to our chain, a new kink. The substitution will be with regards to this: v is equal to tan 2x. Therefore the function with respect to v is equal to sine v, right? Because this sine is attached to this v. The sine is attached to that v. So now look what I do over here. The derivative with respect to u, you write everything else as you're seeing it, and then you start adding in your kinks. See, now I've done du or dv because now I have to bring the v substitution. It is basically sine v, and then derivative of v with respect to derivative of x with respect to x is going to be the rest right here, tan 2x, the portion which actually carries your x variable. Now you know we still have a composite function over here. It's not done. We have to bring yet another substitution. Here was my 1, here's my 2. Let's bring a third one over here. Let w equal 2x. Therefore, the function w would be presented as tan w, right? Tan w. You're seeing that. So now we have to add and elaborate this chain kink of ours. We'll do derivative d over du u square, and then du over dv sine v, and then dv with respect to dw. We have a tan w, and then finally derivative of w with respect to x, we'll have 2x. Now you can see we got 1, 2, 3, 4 kinks into this. 4 kinks. Now all that remains is to find the individual derivatives of everything and then bring them together. Yes, I know I haven't addressed these in my videos, but I will in the future, and you will see all of this come into play. The derivative of u squared will be 2u. The derivative of sine v will be cosine v. And we still have to plug in these uv's and w's at the end. The derivative of tan w would be secant square w. The derivative of 2x is just a 2. Now if you see, we're beginning to take shape over here. Let's bring the coefficients together and start bringing in our variables. 2 times 2 is a 4. And then we have a u over here. U will be all of that. This right over here. You'll get sine tan 2x. Now let's bring the cosine, and its v value, tan 2x. Now let's bring our secant value, secant square with its attached w value, which is 2x. So this right here represents our final answer, all of this. This right here is the derivative of this function over here. Derivative of that. You can see it can get pretty complicated, but if you were to graph this function and then you found this derivative and you plug in the value of a given point on that curve and you solve all of this by plugging in that x coordinate in places of these x, you would get an instantaneous rate of change from which you can start working towards a slope and the equation of a tangent line to that curve. But you can see this was a chain rule in a more elaborate form with multiple kinks and multiple substitutions playing into effect over here. But you can see how it rolls out. As you see, we start learning the chain rule along with the product and the quotient rule. Some of these aspects can get a little more complicated. But this was just for the purposes of showing you how the chain rule can become a little more than just 2 kinks. You should not always be expecting there'll always be a single substitution and that'll be it. Sometimes you can have 3 or 4 or 5 substitutions. So keep all of these things in mind. I hope you've enjoyed this video, because next we'll be talking in terms of our videos with the product rule and our quotient rule. And then we'll bring it all together with a video which might show everything in combination. Before we start tackling the derivatives of the various other functions, please like, subscribe and share. Thank you for watching this video. Have a nice day.